Hey everyone, let's dive right into this explainer. We're going to completely demystify organic chemistry so you're totally prepped and ready to crush your DPET-03 and FSC Class 11 exams. Whether you're starting from scratch or just need to lock down those high-yield facts, we're going to break this all down. And trust me, we'll keep it visual, super direct, and actually easy to remember.
Here's what we're covering today. Intro to organic chemistry. Sources of organic compounds. What are functional groups? The hydrocarbon family, oxygen and nitrogen groups, and a high-yield exam review. We'll be using a what, where, and how framework to keep everything compartmentalized. All right, let's get into it.
Section 1. Intro to Organic Chemistry.
To really wrap your head around the sheer scale of this topic, you just need to think about one word: millions. Literally, millions. Carbon atoms have this unique superpower to link together and form millions of unique organic compounds. I mean, they vastly outnumber all the inorganic compounds combined. It's all because a single carbon atom can form 4 incredibly strong covalent bonds, which creates an almost infinite variety of molecular shapes. So the absolute crucial point here is that this entire field revolves around one specific definition. Organic chemistry is the branch of chemistry that studies compounds of carbon and hydrogen, hydrocarbons, and literally all of their derivatives. Now, sure, a few carbon compounds like carbon dioxide or carbonates are technically considered inorganic for historical reasons, but the vast majority, they are the absolute foundation of organic chemistry. And because we have millions of these things, we have to classify them to actually study them, right? We basically split them into 2 massive buckets. First, you've got open chain or acyclic compounds. Think of straight chain butane. And then you've got closed chain or cyclic compounds, where those carbon atoms link up to form a ring, like benzene. It all comes down to how that carbon skeleton is put together.
Section 2. Sources of Organic Compounds.
Okay, so where do we actually find all these compounds in the real world? Well, you can divide their sources into natural and synthetic. On the natural side, we have absolute treasure troves like fossil fuels, which means petroleum, coal, and natural gas, along with, living plants and animals. And on the flip side, we have synthetic, man-made sources cooked up in labs. We're talking synthetic polymers, plastics, and life-saving drugs.
Now pay attention here, because this is a massive high-yield fact for your exams regarding the industrial importance of those fossil fuels. Natural gas, it's mostly methane, which makes it an unbelievable fuel source. Refining petroleum gives us alkenes, and we literally need those to manufacture modern plastics and lubricants. And coal, that is a huge source of aromatic hydrocarbons, which we use to make dyes, perfumes, and even pharmaceuticals.
Section 3. What are functional groups?
Listen, if you take away absolutely nothing else today, make sure you get this concept. A functional group is an atom or a group of atoms that completely determines the characteristic chemical properties of an organic compound. Think of the carbon skeleton as just a blank mannequin, right? The functional group is the outfit you put on it. That outfit completely dictates what the mannequin's job is, how it behaves, and how it's going to react with everything else.
So, any compounds wearing the exact same functional outfits belong to what we call a homologous series. And because they share that same functional group, they also share similar chemical properties and the same general formula. But here's the catch. As you move down the series, they physically grow heavier by exactly 1 CH2 unit at a time. And because they grow so gradually, they show very regular, totally predictable trends in physical properties, like melting and boiling points.
Section 4. The hydrocarbon family.
Let's look at the foundational outfits, the pure hydrocarbons. Notice how simply introducing a double or triple bond changes literally everything. Alkanes, like butane, only have single bonds. Their carbon valencies are fully maxed out, so we call them saturated. But the second you drop in a double bond, boom, you get alkenes, like butene. Drop in a triple bond, you get alkynes, like acetylene. Because of those multiple bonds, alkenes and alkynes are unsaturated. And that completely changes the game, making them way more chemically reactive than alkanes.
To put this into a real-world perspective, a perfect everyday example of an alkene is beta-carotene. It's the exact compound that gives carrots that super bright orange color. It actually has 11 double bonds in its structure. Plus, it's a completely essential dietary source of vitamin A for us.
Section 5. Oxygen and nitrogen groups.
All right, now let's accessorize these chains. Adding a simple hydroxyl group, that's an OH, to a carbon chain instantly creates an alcohol, like methanol. But if you introduce a carbonyl group, which is a carbon double bonded to an oxygen, you get entirely different families like aldehydes and ketones. You absolutely have to be able to visually spot the difference for your exams. If that carbonyl is right at the end of the chain, hooked up to a hydrogen, it's an aldehyde, like methanol. But if it's sandwiched right between two other carbons, that's a ketone, like propanone.
Okay, here is a classic trap you're going to see on tests: confusing carboxylic acids with esters. Carboxylic acids have a carboxyl group. That's a carbonyl attached to a hydroxyl group. A famous one is ethanolic acid. It's what makes vinegar taste so sour. Esters, on the other hand, have the hydrogen of that acid swapped out for an alkyl group. And esters are actually the compounds that give off those really pleasant, fruity smells you find in foods and perfumes. Moving over to the nitrogen families, you just need to contrast amines with amides. An amine has a basic amino group, which is an NH2 attached to an alkyl chain. Think methylamine. But if you take that exact same NH2 group and stick it directly onto a carbonyl carbon, well, you've just created a totally different functional group called an amide, like acetamide. Honestly, catching these tiny structural nuances is exactly how you ace these exams.
Section 6. High-yield example.
Time to lock this in. Here's our first practice question. True or false? Butane, which is C4H10, and butene, which is C4H8, are structural isomers. Take just a second to think about this before I give it away. Ask yourself, what actually defines an isomer?
The answer is absolutely false. By definition, structural isomers have to have the exact same molecular formula, just a different structural arrangement. Since butane has 10 hydrogens and butene only has 8, there is no way they're isomers. A real pair of isomers would be something like straight-chain butane and branched isobutane. They both share that exact C4H10 formula.
All right, let's try a classic functional group identification question. Look at this structure, CH3, connected to a carbon, double bonded to an oxygen, connected to another CH3. Based on what we just learned, what family is this? Are we looking at an aldehyde or a ketone?
It's a ketone. Specifically, it's propanone. You probably know it better as acetone. We know for sure it's a ketone because that central carbonyl carbon, the one with the double bond to oxygen, is sandwiched directly between two other carbon atoms. If it had been attached to a hydrogen on one side, then, yep, it would have been an aldehyde.
You guys nailed that. As we wrap up this explainer, I really want to leave you with this thought. Carbon's totally unique ability to bond with itself literally gives us the blueprint for life, not to mention the plastics, fuels, and medicines we rely on every single day. So, with millions of molecular combinations already mapped out just by swapping these functional outfits, what chemical boundaries are left for us to push? What crazy synthetic supermaterials are sitting in a lab right now just waiting for the next generation of chemists to discover them? Thanks so much for joining this explainer, and seriously, good luck on your DPA3 exams. You're going to do great.